Hi, it's time for another math easy solution. To discuss further into calculus with parametric curves and look at example 2 of the arc length series and go over the unit circle example again. Recalling example 1, I went over the arc length of a unit circle and I showed that as just the circumference of a circle. In our case, unit circle is just a radius r is equal to 1. So we had the circumference equals to 2 pi. So make sure to watch example 1 to see that. But now we'll do something slightly different. And in this one it states, find the arc length of a unit circle if it is written in the parametric form like this. So this is as well a unit circle. But what happens here, as I showed before, this exact same parametric equations, I went over my earlier video as well, and I showed that this actually traverses around the circle twice. So make sure to check that video out, and I'll put that in a link below. So we have this form: x equals to sine 2t, y equals to cosine 2t, and t is between 0 and 2 pi. So if we apply the arc length formula, so if we recall, L is equal to, from alpha to beta of square root, now we have this one, actually this is dx over dt. Dx over dt squared plus dy over dt, and make sure to watch my earlier videos on arc length to see this proof. So we have this, and for our case our alpha is equal to 0, so from 0 to 2 pi. The beta is equal to 2 pi. Now the dx over dt, well, we could just solve those. So dx over dt, that's a derivative of this variable. That's just going to be equal to cosine 2t, and then using chain rule, add the t in front. So we have cosine 2t, and then for dy over dt, this equals to the derivative of this one. That's going to be negative sine 2t, and then chain rule, put the 2. So we have this equals to negative 2 sine 2t. So now what we could do is, well, we could plug these inside like that, and then start solving our arc length. So L is equal to integral from 0 to pi of, and now of this giant square root, now we have a 2 cosine 2t squared plus, now we have a negative 2 sine 2t squared dt. When we plug those in, negative, when we're squaring it just becomes positive. So what we end up getting, to simplify this further, we get, well, this is going to be 2 squared is 4, so we have a 4 cosine squared 2t, this becomes positive because it's a square, plus 4 sine squared 2t dt. So now what I'm going to do is I'm going to factor out this 4. Yeah, I'll factor it out as well as the square root with it as well. So what we end up having is a integral from 0 to 2 pi. So factor it out, we'll have a square root 4 times it by a square root of, now we have an cosine squared 2t plus sine squared 2t. So we just take the 4 out of it, and then we get square it by itself like that, dt, and now that's just 2. So that just goes to 2, because square root of 4 is just 2. And now what we have is, well, we can apply the trig identity, or the Pythagorean trig identity. So recall, or actually before I do that, what we'll do is let theta equals to 2t, and recall, so we just let that equal to 2t, that's just theta, and recall trig identity. So recall the trig identity, I'll put the link in the description below. Yeah, so check that one out. And basically we have cosine squared theta plus sine squared theta just equals to 1. So that's just the identity, and then doesn't matter if this is 3t, 5t, if they're both the same, this always equals to 1, like that, just by using this substitution. So now we could throw this inside, and square root 1 is just 1. That's 2. So what we end up having is L is equal to the integral from 0 to 2 pi of 2 dt, because 1 square root 1 is just 1. Now this equals 2. Just evaluate as the constant, so we have 2. We could just take that out, so then we have it t, and then we have it from 0 to 2 pi. This equals 2. This just equals to, well, 2 pi there, minus 0. So we have 2 times by 2 pi equals 2 4 pi. Yeah, now what's important to notice is, as I explained before, this is rotating around that unit circle twice, so then we get twice the circumference, or 4 pi. And again, notice that the interval gives twice the arc length of the circle, because as t increases from 0 to 2 pi, the point sine 2t, cos 2t, these are just the xy variables, xy traverses the circle twice. Again, I've done this in my earlier video. I'll put the link in the description below, so check that out. In general, when finding the length of a curve C from a parametric representation, we have to be careful to ensure that C is traversed only once as t increases from alpha to beta. Otherwise, we'll get a distance that's more than it actually is, because it's rotating it about multiple times. For example, in this case right now, if you were to graph it, what we end up having is, if this is from x and y, let's say we have a unit circle, just a circle of radius 1, so r equals to 1 as distance from here to here, or just to extend this past this point like that. Yeah, so if we have it like that, and then I'll just erase that arrow just to make it a bit neater. So now what we have now is, if we have a point here at the sine 2t cos 2t, and it traverses around this, well, twice. Once is 2 pi, and then it goes all the way around to here. So if you start off from that point, this is a total of 4 pi. And that's the arc length, because it's rotating around it twice. And that's why it's always important to be careful that we know the exact interval that we're changing from, and to make sure that the curve C is traversed only once, or only just once completely, not portions of or more than once, like 1.5 or 2, etc. So anyway, that's all for today. If you learned from this quick example on parametric curves, and to show you how it's different from regular curves when finding arc length, because you might be basically reinventing the wheel and finding a higher arc length than actually can. So you always have to make sure you're doing this right. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another math easy solution.